Hey everyone, this is Dr. Walker. Video 241, we're going to talk about the other one of Kirchhoffs' rules, the loop rule. We just finished talking about the junction rule. So, the loop rule says that the sum of all potential differences around any closed circuit loop must be zero. If we want to write this as an equation, we would say the sum of all the potential differences equals zero. Let's take a look. We have in this circuit here, we have a battery that's providing the energy for our charges to move. So as our charges move through each of these are resistors here, and they all have a potential difference across them because we know that delta V equals I times R from Ohm's law. As they move across, as the charges move through the resistor, they lose energy, lose more energy down here, lose more energy down here. So you start at a high potential, and by the time you get through all the resistors, you're back to your zero potential, and then you get more energy through the battery, and then you start the cycle again. So all of the potential differences across the three resistors, or whatever devices that you have, must equal to the potential difference provided by the battery. So this is very similar to when we said when we had resistors in series that the voltages added up to the battery voltage. So I do want to note that this is a result of conservation of energy. In the previous video, I forgot to explicitly state it. It was on the notes. I'm going to go back to it real quick just because I forgot to specifically mention it. That junction rule, that was a result of conservation of charge, right? The fact that the current in equals the current out is because whatever charge goes in must come out. So forgot to say that earlier. Okay, so back to this. Let's see how we can use the loop rule. First, we have to obey these sign conventions, what's positive and what's negative. You're going to have a loop in your circuit, and you're going to go across that loop. You're going to go in a circle around that loop and examine all the resistors in that loop and examine the potential difference across each one. So, as you're going around your loop, if you're going in the same direction that the current is going, then that potential difference across that resistor is going to be negative. If you think about it, if you think about a circuit with just one resistor, then this will make sense. If you have 0 volts here and 9 volts here, you know that you have 9 volts here and 0 volts here because of the equipotentials. So we know that the current is going clockwise because it goes away from the positive terminal. So if we're looking at this resistor and we're crossing it downward in the same direction as the current, which is also going down, this rule is saying that our potential difference is negative, which makes sense because we're going from a high voltage to a low voltage. Okay, so the opposite applies. If you cross a resistor in the direction opposite of the current, then you're going to gain potential. So you can draw the circuit again just to make sure that that makes sense to you. And then if you cross the EMF source from the negative terminal to the positive terminal, once again you have a positive potential difference, and it's just going to be equal to the EMF of the battery. There's not going to be any internal resistances to these batteries. So it makes sense as you go to the right from the negative to the positive terminal that you're gaining a potential because the charges are gaining energy. And finally, if you cross your EMF source, your battery, from the positive to the negative terminal, then you're going to lose voltage. So you do need to remember these rules so that you can use them when you use the loop rule.